How is energy wasted as a box skids to a stop? The answer to that question is that sliding friction transforms the box's kinetic energy into thermal energy. But what is thermal energy? What sort of process carries out that transformation? Explaining those issues is the purpose of this video. When I slide a box across the floor, something strange happens to its energy. I do work on the box, pushing it, and it moves in the direction of my push, so I'm transferring energy to it. It leaves my hand with that energy mostly in kinetic form, the energy of motion. But then it encounters the floor. Moments after hitting the floor and sliding across it, the box is motionless. What happened to its energy? As the first step in solving that puzzle, I'll ask you a question. When a box slides to a stop on a motionless floor, which object does work on the other? The floor does negative work on the box, and that's it. The floor pushes the box in the direction opposite the box's velocity. And so the box, in this case, is moving to your left as the floor is pushing the box to your right. So the floor is pushing in the direction opposite the box's motion. So the floor does negative work on the box. At the same time, the box is pushing on the floor, but the floor doesn't move. So the box does no work, zero work on the floor. All that's happening then is the floor doing negative work on the box, taking energy out of the box and destroying it, getting rid of it? Well, no. The energy is still conserved, and we have to look for where that energy goes. Sliding friction can't violate the conservation of energy. The box's energy has to remain somewhere in the universe, even after it slides to a stop. What happens to that energy is that it's ground up into tiny portions that are dispersed randomly among the particles that make up the top of the floor and the bottom of the box. Energy is still there. It's just distributed in such tiny pieces that you don't notice it normally, except by way of the temperature of those two objects. To help you visualize this idea of grinding ordinary energy up into tiny random fragments, here's a series of simple demonstrations. First, I'll roll a metal ball into a handful of other identical balls. I'll do work on the first ball when I push it forward as it moves forward, so it will have energy in the form of kinetic energy as it rolls across the table. When it strikes the other balls, however, its energy will be dispersed among those balls. So here we go. So the energy's all still there. I mean, these guys don't roll perfectly, so they will eventually stop. But my energy put into one ball was then dispersed among many balls. Here's the same experiment, but with smaller balls and many more of them. Let me get this guy going and ready. Off it goes. The energy's still there. It's just dispersed among lots of balls. And now I have even tinier balls. There are hundreds of them, and they're going to share the energy that I invest in this first ball when I get it moving initially. So here we go. I'll start the ball rolling. It dispersed its energy among all those balls. Well, the energy is still there. They're losing their role after a while because things aren't perfect here. But you get the idea that you can start with energy that's equivalent to work. I did work on that one ball. The ball's got that energy in the form of kinetic energy. It can do things. But once it crashes into this myriad collection of balls, the energy's all dispersed, spread out among lots of little balls, each doing its own thing. I could keep going. I could go down to sand, I could go down to dust, and finally I could go down to the atoms and molecules themselves that make up materials. And once you've dispersed the energy into that vast collection of particles, each one doing its own thing with its own tiny dose of energy, You can't do very much with that energy. That energy now is so disordered, it's so randomized, that you can't get it all organized again to do useful work, not directly. This glass dish contains a very orderly arrangement of beads. All the purple beads are on one side, all the white beads are on the other. And this kind of order doesn't happen by chance. Think of your sock drawer. If you only have two colors of socks, purple and white, and you just dump them at random into your drawer, you don't end up like this. It's all mixed up. You have to sort them to end up like this. So this arrangement, not a chance arrangement. And it's not forbidden, strictly speaking. The laws of probability make it extremely unlikely. It could in principle happen, but in practice, it's so unlikely you never ever have it happen by chance. I sorted these before filming this, and I don't want to mix them up very often because I'm going to have to sort them again. I'm not going to be able to sort them just by chance. I'll show you. Ready? Here we go. I'm going to mix them. I'm not looking. Yay! And voila! All scrambled. Can I sort them by stirring again? They're still messed up. It's hopeless. Once you've let the randomness in and you've evolved to a more disorderly arrangement, there's no undoing it. The laws of probability are against you. If all this talk about probability brings to mind gambling, you're thinking along the right path. There is a reason why you're not likely to win the lottery even once, and why no one ever wins the lottery 1,000 times in a row. Although technically possible, it's so unbelievably unlikely that it simply never happens. This glass dish now contains about 50 dice, and they're all ones. Do you think that happened by chance? Let's see if I give this a shake, what happens to this orderly arrangement of dice. Here we go. Oh, look! It's not all ones anymore. What do you think? What about if I show you another shake and see what you think of this? All ones! Wow, I'm pretty tricky. That outcome is so fantastically unlikely that you know I reversed the video. I cheated. Once I disordered the dice, there was no simple way back. In all of these demonstrations, the laws of motion, Newton's laws, have been silent. Those laws deal only with things like forces and accelerations and have nothing to say about the return of order from disorder. The demonstrations, therefore, have been all about probability instead. This brings me to a question about a familiar nursery rhyme, Humpty Dumpty. Spoiler alert, Humpty Dumpty is an egg. Humpty Dumpty has a great fall and he breaks. And according to the rhyme, all the king's horses and all the king's men couldn't put Humpty together again. So the question is this: if dropping Humpty once broke him, why won't dropping him again reassemble him? Dropping Humpty Dumpty a second time wouldn't reassemble him because it's simply too unlikely. The laws of motion will allow for that reassembly if all the yolk and all the white and all the shell pieces all move just right, following the laws of motion and the forces and the accelerations and all that. Humpty will reassemble. The odds of that happening are just fantastically small. It never, ever, ever happens. So, poor Humpty is out of commission here, not because the laws of motion forbid it, but because the laws of probability do so. So sliding friction takes the energy of one or two large objects, say the box and the floor, and grinds up that energy into tiny random portions that are then dispersed among the particles that make up those two objects. Ordered energy, that is energy that could easily do work, has become disordered energy, energy that can't do work very easily. It's a one-way street, and there's no simple route back. How do we know that this disordered energy even exists, though, and what role does it play in our lives? It's known as thermal energy, the disordered energy associated with temperature. Sliding friction increases the temperature of the surfaces as they slide across one another. You can observe this effect fairly simply just by rubbing your hands together. If you press your hands tightly together and slide them across one another, you'll feel your skin getting warmer. Your muscles are doing work on your hands, pushing them in the direction that they move, and sliding friction between your skin is grinding that work up into tiny pieces, thermal energy that's still in your skin, and you feel warmer. Now, some people may be able to start a fire simply by rubbing two sticks together. That is, using the sliding friction between those sticks to turn enough ordered energy into thermal energy to heat the surfaces of the sticks until they ignite. I'm not one of those people. I can't pull off that trick. However, with some help, I can make wood rubbing against wood start a fire. And what I've got now is a jig that holds a round wooden peg, a piece of dowel about that long and about ½ an inch in diameter. And it's pressed between two pieces of wood, so it sits in sockets in those two pieces of wood, and I'm going to spin that peg using a bow, an archery bow. And I've wrapped the bow's string once around the peg so that it grabs the peg using static friction, actually. And as I push the bow toward you and away from you, the peg will spin, and its surface will rub against the wood at the other end of the socket. So, here we go. I'm going to begin moving the peg using the bow. I hope you can see all the smoke. I can get it to the point where it will ignite, probably with a little help from tinder, something that really burns easily. But the basic idea is here. I got that wood so hot that it's smoking vigorously. And it is therefore possible to start a fire by rubbing wood against wood and using sliding friction to turn ordered energy into thermal energy. We've seen that sliding friction grinds up energy. It turns useful ordered energy into much less useful thermal energy. But sliding friction also grinds up the surfaces themselves. It wears them out. That wear isn't very noticeable when you simply rub your hands against one another, but you do notice it in the soles of your shoes after months of scuffing them on the pavement. And those soles wear the surfaces they scuff against. Take a look at an old stone staircase, one that has handled many feet for many years, and you'll see wear. Sliding friction can even wear out steel. This is a piece of tool steel, a metal so hard that it can cut nearly any other metal. Machinists shape tool steel by wearing it away. They use a grinder and sliding friction to take away parts of the material and give it shape. Now, this grinder will spin the wheels very fast so that their surfaces will move past and slide against the tool steel at hundreds of miles an hour. And they'll wear away that metal rather quickly. Here we go. It takes a few seconds for the grinder to get up to speed. I've started it spinning. There it is, up to speed. And now I'll take the piece of tool steel and put it against the fast-moving surface. It's cutting away the metal and shooting sparks. So, as you can see, you can shape the metal using sliding friction. This is also now getting very hot, so that's why I stopped. I normally would cool it off periodically in water, but I did a little bit of shaping, cut away a little metal using sliding friction. Sliding friction wastes energy and wears out surfaces. But what about static friction? In principle, static friction wastes no energy and causes no wear. When the surfaces don't slide across one another, static friction instead transfers energy perfectly from one surface to the other. For example, if I push on this box and try to get it sliding, but don't, so it doesn't actually slide at all, there's no energy transfer at all between the box and the floor. In fact, the two objects do no work on one another, either positive or negative, because neither one moves a distance. So there were forces between the box and the floor, but that's it. No distance traveled and therefore no work done. No energy wasted. Another example is when I lift a beverage can in the usual manner. I just used a static frictional force to lift the can. You know it's a static frictional force because it's an upward force. I'm supporting the can's weight as it moves upward. And for a force to be upward exerted by my finger on the can, that has to be a frictional force. It's parallel to the surface of the can. If there were no friction, the can would slip right through my fingers to the ground. So I exerted an upward frictional force, static frictional force on the can as the can moved upward. I did work on the can. At the same time, the can did negative work on me. It pushed my fingers downward as my fingers moved upward. That's negative work. And the amount of negative work the can did on me is exactly equal to the amount of positive work I did on it. Overall, static friction perfectly moved energy from me to the can and didn't waste any of it. On the way down, static friction moves energy from the can back to me. Again, no waste. So there's a pretty clear distinction between the world of static friction and the world of sliding friction. Static friction wastes no energy and causes no wear. Sliding friction, on the other hand, does waste energy and does cause wear. Well, this episode is about wheels. And the purpose of wheels is to avoid wasting energy and wearing out surfaces. So the problem that wheels solve is not static friction. Static friction is okay. The problem is sliding friction. And wheels, it turns out, get rid of sliding friction, but keep all the good features of static friction. And that's what we'll see in the next video.